Alright, so today let us talk about plasticity and structure of soil. Okay, when clay minerals are present in fine-grained soil, the soil can be remolded in the presence of some moisture without crumbling. So this cohesive nature is caused by the absorbed water surrounding the clay particles. In the early 1900s, a Swedish scientist named Atterberg developed a method to describe the consistency of fine-grained soils with varying moisture contents. So we have here no, in the illustrations, we can observe that we have different kinds of consistency in our soil. The very evident one is this one. Now we can see that the soil has turned into a mud through the presence of a large amount of moisture. And then in here, we can see, or we can consider, or we can interpret this picture as a soil with low or very low moisture content because it is still looking like dry. No, you can still identify its grains without that are not sticking together. So you also have here an example of a consistency of soil. You also have here, no, it looks like a solid. The soil has become or has appeared like a solid in here and as well as in here, no. So at a very low moisture content, soil behaves more like a solid. So when the moisture content is very high, the soil and water may flow like a liquid. So hence, on an arbitrary basis, depending on the moisture content, the behavior of soil can be divided into four basic states. We have the solid, the semi-solid, the plastic, and the liquid. So um, we can see here now the first state of the soil is the solid. So it still has a very um, a resistance to stress. No, it still can withstand a load. And then as the moisture content increases, no, along with this line, what if the moisture content reaches its shrinkage limit? So mo ni siya dihang apart, no. So um this is the limit that the soil will retain its volume without change in its volume, no. So beyond this, beyond the shrinkage limit of the soil, it will behave like a semi-solid, no. um Semi-solid consistency of soil. In this consistency, no more kneading is possible and the volume decreases as the sample dries up. So in the shrinkage limit, the soil does not change its volume. So beyond that, the soil now becomes semi-solid or behaves like a semi-solid. So it's there is already a possibility that the soil will change its volume or will decrease its volume. So as again, the moisture content decreases and then it reaches its plastic limit, no? This is the minimum moisture content that the soil will start to behave as plastic, no? So murag diri nga part, murag gamay na lang gyud ang iyahang ability uh, sa iyahang load resistance, no, characteristics, gamay na lang gyud, no. So diri nga parts between the semi-solid and the plastic, the soil can still resist an amount of stress or load pero gamay na lang gyud, no. So sa gamay nga load, kibali gamay nga stress, no, dako na yang strain. So and then from the plastic state, no, from the plastic limit, the moisture content continues to increase. So it will reach its liquid limit, no. Liquid limit, in this limit, it is the start or it is the minimum moisture content that our soil will start to behave liquid. So in this part, no, the soil can no longer resist stress. So mag-strain na siya diretso, no? Even in a very low or zero stress, mag-strain na siya diretso. It will undergo strain already. So liquid, no, consistency is a behavior of soil that is similar to a fluid or a liquid mud. So we know, no, kay as much as we have observed in the actual, kano, when it rains, and the soil becomes saturated, meaning its moisture content actually increases. So that is why our soil behaves like a liquid because of too much presence of water. So therefore, in the consistency or in the plasticity of soil, the amount of water or the amount of moisture present in our soil plays a very big uh, contributory factor to that, no? It is one of the major good factor or reason why our soil will undergo a different state or different consistencies. It is due to the moisture content. So I hope we are clear on that. Okay, we have the Atterberg limit. So let us talk about what are the Atterberg's limits. So we have the liquid limit, the plastic limit, and shrinkage limit as mentioned on the previous slide. So what are these limits, no, and who have established them and what are their uses? So the consistency and behavior of a soil is different in the as the engineering properties at varying degrees of moisture content. Thus, the boundary between each state can be defined based on a change in the soil's behavior. So Atterberg limits can be used to distinguish between silt and clay and to distinguish between different types of silts and clays. So these limits and tests were developed by Albert Atterberg. Um, uh, he is a Swedish agriculturist and later were refined by Arthur Casagrande. So two people, two great men have contributed to this limits, no, to the establishment of these limits. These tests can be used in evaluating various soils, which will ultimately have structures built upon them. So soils, when wet, retain water. I know, when soils when wet retain water and some expand in volume. The amount of expansion of a soil is related to the ability of it to absorb water and its structural makeup. So Atterberg tests are mainly used on clayey soil or silty soils since they are the soils that most affected by expansion and shrinkage due to varying moisture contents. Thus, the Atterberg tests are used widely in the preliminary design stages of structures, ensuring that the soil will have the correct amount of shear strength and will exhibit minimal change or in volume as it expands and shrinks with different moisture contents. So it is said here, Atterberg limits or Atterberg limits test is only used or most of the time, no, mainly used for clayey soils and silty soils, meaning fine-grained soils only. Kaya syempre, those coarse-grained material like the sand and the gravel, they do not have man the characteristics of absorbing water. So meaning their consistency will not be affected by any change in the moisture content or any change in the water content. So a simple example of that, no, we can even wash our sand, no, without changing its consistency. When you submerge an amount of sand into water and then you take that sand out of the water after submerging it, the sand will remain as a sand. It will not have a volume change, or it will not even solidify, or it will not even liquefy due to the introduction of water to it. So, Atterberg's limit tests are only conducted to those type of soils that can be affected and or that can undergo volume change under the presence or under the change in moisture content. So um, the purpose of Atterberg test, no, is to be able to identify the amount of water nga enough to prevent it, no, from large volume changes, no? Kay volume changes in our foundation can really cause failure or major problems to our structures over it. So that's why it is very important for us to know the correct amount of water so that we can get the desired shear strength of our soil. Kay since soil magyud or fine grained soils are very sensitive to water changes, no, to earth its moisture content, so its behavior solely or not or mainly relies on the on its moisture content. So that's why our job is to make sure nga the soil only has its desired or correct or enough moisture content so that it does not become liquid, no, or it does not change its volume. So that is somehow the purpose of the Atterberg limits test. So let us talk about the first of the Atterberg limits. Let us talk about the plastic limit. So the percentage, it is the percentage moisture content at which a soil changes with decreasing wetness from the plastic to semi-solid consistency, or with increasing wetness from semi-solid to the plastic consistency. For the conduct of the plastic limit test, we follow the standard test method set by the ASTM with code, or the test code is D4318. So ASTM stands for American Society for Testing and Materials. So this is the standard, no? This code um, provides us of the standard procedures that we have to follow in the conduct of our plastic limit test. So, plastic limit is a test that involves rolling out a thread of fine portion of the soil on a flat, non-porous surface. So, mura kag maglugod, no, or i-roll nimo ang soil on a flat or non-porous surface. For this material, we use a glass, no. Atong gagamitin is kanang mar siya bildo lang siya nga flat. Or mara glass plate lang siya, no. And then dito nato lukuton ang soil. So, the procedure is defined in ASTM standard D4318. So, if the soil is at moisture content where its behavior is plastic, this thread will retain its shape to a very narrow diameter. So the sample can be remolded and the test repeated. So as the moisture content falls due to evaporation, the thread will begin to break apart at larger diameter. So the plastic limit is defined as the moisture content where the thread breaks apart at a diameter of 3.2 millimeters. Soil is considered non-plastic if a thread cannot be rolled out down to a 3.2 millimeters at any moisture possible. So, in the plastic limit test na very simple lang iyahang concept, no? Magkuha lang the amount of soil and then dungagan na nimo siya water. So, random lang to nga amount sa water, dili pud kaayo daghan and dili pud kaayo gamay. So, it would be better nga gamay lang sa imuhang idugang because throughout the test, mag-trial and error man kaana, no? You will have to repeat the test at every moisture content sa dungag-dungagan nimo to ang water nga imong gidugang dito sa katong sa imong soil sample, no. Tapos imong goal is to be able to roll out, no, the soil into a 3.2 millimeter. So dapat imo siyang ang lukuton, no, lukuton nimo ang soil kay since um if the moisture content is enough na for the soil to behave plastic, syempre malukot na nimo na siya, no, dito sa glass plate. Dayon imong goal is dapat sa imong paglukot-lukot ang imuhang soil dapat maabot siya to 3.2 millimeters. Meaning mao to ang iyahang kato nga moisture content nga naa atong soil kay mao to siya ang imuhang plastic limit sa imuhang soil. Kay what if lugar dili man ka diretso maka roll sa imuhang soil into 3.2 millimeters. Kay what if in cases like dili pa enough ang imong water nga gidugang sa imong soil, dili man nimo na siya ma-roll into 3.2 millimeters, no? As the moisture content falls due to evaporation, the thread will begin to break apart at larger diameters. So, sa dili pa siya maabot sa diameter nga 3.2 millimeters, mo mo break na siya, no? Mabugto na tong imuhang gi-roll nga thread sa, although I will be showing you how it looks like, no? Mabugto na tong imuhang gina-roll nga nga yuta. And then in that case, kung wala pa siya naabot sa 3.2 millimeters and then nabugto na siya, no? Ang kat imong gina-roll out, you will have to repeat the test and add water to it. So para um ma-roll out nimo will become, as the soil becomes more plastic, and then ma-roll out nimo siya into 3.2 millimeters. So we also have here, kung dili gyud nimo ma-roll down into 3.2 millimeters ang soil, meaning ana sige balik gi-repeat na nimo kadaghan gyud ang imuhang test, nagdugang nakaog ka ng nagkanlain-lain nga amount sa imong moisture, and then dili pa gyud siya ma-roll into 3.2 millimeters, we can conclude that the soil is non-plastic. Alright, so now we have here the apparatuses that we need for the conduct of the plastic limit test. We have the graduated cylinder, which is this one, with a glass plate, kani, this one, kaning murag, flat lang siya, no, nga glass. And we also have the spatula, the moisture can, and the mixing bowl. So, diri nato i-mix, no, ang soil o ang water using the spatula. And then, diri dayon sa kaning glass plate nato i-roll ang yuta. And then, if we are able if we are already able to roll our thread of soil into the diameter of 3.2 millimeters, and then we will take a sample out of that, or out of the thread, and we will put that into our moisture can for the determination of the moisture content. And for the determination of the moisture content, mo lang gyapon, no, we can still use the oven drying method for the determination of moisture content of that soil, and that moisture content of the soil will be the plastic limit of the soil sample. So let me present to you, no, a brief overview of what the procedure really at the plastic limit will be about. So muna akong ginaingon, no, i-roll nimo ang soil into a thread, and then um, you will aim to roll it into the diameter of 3.2 um, millimeters. So we take about 8 uh, milligram of this plastic soil mass and roll it between fingers and the glass plate with just sufficient pressure to roll the mass into a thread of uniform diameter throughout its length. So the rate of rolling shall be between 80 to 90 strokes per minute. So continue rolling till you get a thread of 3 millimeters diameter, or 1/8 inch. So Casagrande defined the plastic limit as the water content at which a thread of soil just crumbles when it is carefully rolled out to a diameter of 3 millimeters, or 3.2, no? So if the thread crumbles at diameter smaller than 3 millimeters, the soil is too wet. So if the thread crumbles at diameter greater than 3 millimeters, the soil is drier than the plastic limit. So the sample can then be remolded and the test repeated. So once the appropriate size rolls are made, their moisture content is assessed during the procedure described previously sa katong oven drying method, no? So now let us talk about the liquid limit, or the liquid limit test. So this is the second limit, no, by Atterberg. So liquid limit is the water content where the soil starts to behave as a liquid. So liquid limit is measured by placing a clay sample in a standard cup and making a separation or a groove
using a spatula. So the cup is dropped till the separation vanishes. The water content of the soil is obtained from the sample. So again, the standard test method for this test is still the ASTM D4318. So the liquid limit test defined in ASTM D4318 determines the water content at which the behavior of a clayey soil changes from plastic to liquid. However, the transition from the plastic to liquid behavior is gradual over a range of water contents, and the shear strength of the soil is not actually zero at the liquid limit. So the precise definition of the liquid limit is based on the standard procedures. Liquid limit can be determined using the Casagrande cup method, so which is usually are used in the United States with a cone penetrometer, which is more prevalent in Europe. So there are two ways, no, to determine the liquid limit of a soil. It is through the Casa Grande cup and through the cone penetrometer. So I will discuss to you the Casa Grande cup method. So these are the apparatuses that we will be using, no, in the determination of our liquid limit. So muna siyang ginatawag og Casa Grande cup, and then mao ni siyang ginatawag nga groove. So we have here another illustration, no. This cup is the same with this cup. So mara gidrawing lang siya to um, reflect the dimension. So muna siyang ginaingon, no, diri ibutang ang yuta dere sa cup. Nana lang siya kadaghan na. And then you will create a groove sa tunga ani nga yuta nga naa dere using this grooving tool. So we will discuss that further, no. Okay. So the other apparatus that we will be needing aside from the Casagrande cup and the grooving tool are the graduated cylinder, of course, for us to be able to measure the water, the spatula, and the mixing bowl para it will allow us mixing of the soil sample and the water, and also the moisture can for the determination of the moisture content, no. So similar lang yapon siya sa plastic limit nga mag-trial and error gyapon ka sa kadaghanon sa imong tubig, no, bantog the graduated cylinder, the mixing bowl, and the spatula is an apparatus are the apparatuses that are common in both the tests. Kay in both the tests man good, we will be having a trial and error in the addition of the water to our soil sample. Okay. In the Casagrande cup method, the soil paste is placed in the Casagrande cup and a groove is made at the center of it. So we can see here, no? Ibutang ang yuta dara, and then we will make a groove at the center. So the limit is defined as the moisture content in percent required to close a distance of 0.5 inches along the bottom of a groove after 25 blows in a liquid limit device. It is difficult to adjust the moisture content in the soil to meet the required 12.5 millimeters or 0.5 inch closure of the groove in the soil path at 25 blows. Hence, at least 3 tests for the same soil are conducted at varying moisture contents with the number of blows varying between 15 and 35. So first thing that you would have to do is mix the soil and the water, and then once done, you place the soil in the Casagrande cup. And then you create a groove at the center of it, no? Yun ano yung itsura. So, inanaw na siya pag groove. Ipaagi lang nimo sa tunga sa cup ang katong grooving tool. And then, the liquid limit daw is the moisture content it requires for this groove to close at 25 blows. So, during this, in this Casagrande cup, no, ang kani nga cup, na-rotate diri, and then, the cup will be brought up and down, mara siya itaktak, no, diri, while kani siya nga lever diri is i-rotate. So ang tawag atong pagtaktak dani, up and down lang siya, no, ang kaning Casagrande cup. Ang tawag ana is kada isa nga taktak niya is blow ang tawag, one blow. So ang liquid limit daw is the moisture content nga naa sa soil nga pagka 25 blows ko no sa Casagrande cup mo close siya og inani. So you might have wondered nga how do you kanang saan gyud nimo pag-target nga sakto ra gyud ang moisture content para mataktak siya after 25 blows. So medyo lisod na siya. So that's why in the procedure you will just then be asked to record the moisture content that it would require the groove to close at 15 to 35. So, pwede siya at 25, at 20 blows, at 26 blows, or 30 blows, or pwede na po siya 17 blows. No, i-record lang to ni mutanan ang moisture content sa soil nga maka-close ani nga groove, no, corresponding to its respective number of blows kung kano siya ni sulod, ni close, I mean. So, after that, no, masyang ginayon, cut the groove at the center of the saw. Lift the cup and drop it a height of 10 millimeters using the crank-operated cam. So, measure the water content required to close a distance of, may na siya. Then, repeat the procedure at least 3 times. So, for example, maka-record ka og ni-close siya at 15 blows. Nakarecord na pod ka, ikaduha ni mga trial, ni-close na pod siya after 22 blows. At then, gidungagan na pod ni mag tubig, then gibutang na po nimo sa Casa Grande cup, no, and then gitaktak na po siya, and then naka-record ka o for example butang na 30 blows nga ni close siya inani. So you just have to record that, and then plot the moisture content of the soil in percent and the corresponding number of blows on semi-logarithmic graph. So, draw the best fit straight line through the plotted point. So, the moisture content corresponding to blows nga 25 or N25, determined from the curve is the liquid limit of the cell. Mo tong giingon ako ganyan, no? For example, natay 15 at 15, so mo ni siya, no? The x-axis is the number of blows, and the y-axis kay mo ni siya ang mga corresponding moisture content. So, for example, para sa ganyan naka-record ta og um, at 15 blows ni close siya, no? Pinakauna nga trial, so i-plot nimo ang corresponding moisture content. So, at naka-record na pod ka, next trials, after the trial for 15 blows, gidungagan na pod nimo tubig ang soil, and then gibutang ni pod nimo balik sa Casa Grande cup, and then after repeating the procedure, na-close na pod ang groove at 20 blows. So, na siya corresponding nga moisture content diri. And then, after sa imuhang katong trial nga ikaduha, idungagan na pud nimo og tubig ang soil sample, and then you repeated the procedure, and then nabantayan nimo nga ni close na pod ang groove at blows nga 40. So you have to graph that, no, in semi-logarithmic graph, and then ang moisture content i-project dahil nimo ang 25 blows diri. Project mo dadto, and the moisture content corresponding to that will be the liquid limit of our soil. So although there is a calculator technique for this one in interpreting this data, I will be discussing it to you in our upcoming synchronous session. Okay. Aside from those two, we also have the plasticity index, also a plasticity property of soil. Pero diri nga part wala na tay test nga i-conduct. So, nalang tay formula nga gamiton. So, first let us talk about what is plasticity index. So, plasticity index is expressed in percent of the dry weight of the sample. So, it shows the size of the range of the moisture contents at which the soil remains plastic. In general, the plasticity index depends only on the amount of clay present. So it indicates the fineness of the soil and its capacity to change shape without altering its volume. So a high plasticity index indicates an excess of clay or colloids in the soil. So its value is 0 when the plastic limit is greater or equal to the liquid limit. So the plasticity index also gives a good indication of compressibility. The greater the PI, the greater the soil compressibility. So the plasticity index is simply the difference between the liquid limit and the plastic limit of soil. So, muna yung formula, no? I-minus lang to nimong LL o ang PL nga imong nakuha from the Atterberg's limit. So according to Burmester, we can classify or characterize our soil based on its pI. So if the soil's pI is 0, we can classify the soil to be non-plastic. So kung 1 to 5, it is slightly plastic. So kung 5 to 10 yung pI, it has a low plasticity, and then so on and so forth. And then the pI, if it is greater than 40, the soil is considered to have a very high plasticity. So the greater the pI, the higher the plasticity of the soil. So we also have another type of limit from the Atterberg's provision. It is what we call the shrinkage limit. So makita man nato kaganyan, no? We have the liquid limit and the plastic limit where we have already discussed. We also have the shrinkage limit. So soil shrinks as moisture is gradually lost from it. With continuing loss of moisture, a stage of equilibrium is reached at which more loss of moisture will result in no further volume change. So the moisture content in percent at which the volume of the mass ceases to change, volume of the soil mass rather, ceases to change is defined as the shrinkage limit. So makita nato diri no, kung mauni siya ang volume of the soil from volume from the volume ang kay nasa y-axis, no, and then the moisture content is on the x-axis. So from, for example, this is i-consider as volume initial magkabali na yung solid phase of the soil. So as the moisture content increases, it is at the shrinkage limit nga dili siya mag-change ang volume sa atong soil. Kaya from the solid, for example, the volume has remained constant now throughout the increase of the moisture content. And then, at the shrinkage limit, rather, there is siya nag-stop. It is the point where the soil mass ceases to change its volume. So, beyond the shrinkage limit, mag-change na dayon ang volume of the soil with respect to the increase of moisture content. So, same as through that, if we move towards the left, for example, we have the initial volume, and then you decrease the moisture content, no? We will now be moving towards the left, and then when we reach the shrinkage limit, beyond that, dili na siya mo change ang iyang volume, no? So, kung say moisture content diri kung bisan pa og kung say moisture content diri rather, mo na siya iyang shrinkage limit, meaning beyond that, any decrease in the moisture content will no longer cause any volumetric change in the soil. So, mo na pasabot sa tong shrinkage, no? However, the standard procedure for determination of our shrinkage limit is now different from the Atterberg's limit test, no? Katagan niya the ASTM D4318 man to. And then this one, no? The test method for shrinkage factors of soils by the mercury method. The standard test for that is the ASTM D427-04. So meaning this provisions indicates the standard procedures that we need to comply with in order for us to conduct with our shrinkage limit test. So let me give you an overview of the shrinkage limit test now. Shrinkage limit tests are performed in the laboratory with a porcelain dish about 44 millimeters in diameter and about 12.7 millimeters high. The inside of the dish is coated with a petroleum jelly and is then filled completely with wet soil. So excess soil standing above the edge of the dish is struck off with a straight edge. So the mass of the wet soil inside the dish is recorded. The soil pat in the dish is then overdried. The volume of the overdried soil pat is determined by the displacement of the mercury. Because handling mercury may be hazardous, so we also have what we call ASTM D4943, which describes a method. So because handling mercury may be hazardous, ASTM D4943 describes a method of dipping the oven-dried soil pat in a melted pot of wax. So the wax-coated soil pot is then cooled. Its volume is determined by submerging it in water. So mao ni siya no ang ah, soil pot before drying, and then after drying ni-shrink na siya no. There is a change in the soil mass and a change in volume. So ang kaning initial volume and initial mass, kita mo siyang M1, and then the soil volume is now V final and the soil mass is M2. So we just have to use this formula for us to be able to compute for our shrinkage limit. So M1 minus M2 over M2, no? So M initial and the final mass after drying, multiply that by 100, and the volume initial, volume before drying, minus the volume final, the volume after drying, divided that by the mass 2, and then multiply that by the density of water times 100, and the outcome from this formula will be our shrinkage limit for the soil. We also have what we call the shrinkage ratio. So it is the ratio of the volume change of soil as a percentage of the dry volume to the corresponding change in moisture content. So the formula is just this one, no? Shrinkage ratio, SR, is equal to the volume initial minus volume dried over the volume dried times 100 over the weight 1, or the weight initial, minus the weight final, or the weight shrinkage. So we also have what we call the liquidity index, still formula based, no? The liquidity index is the relative consistency of a cohesive soil, and the natural state can be defined by a ratio called the liquidity index, so, which is given by this formula. We have here the moisture content, no? The which is the in situ, or the actual with moisture content, minus the PL over LL minus PL. So another index that is commonly used for engineering purposes is the consistency index, or the CI, which may be defined as this formula, no? CI is equal to LL minus the in situ moisture content over LL minus PI. So formula based lang siya, no? Kay from the previous test conducted on our soil, we have already identified the liquid limit and the plastic limit, and also we have already determined the PI through our LL and PL, and the in situ moisture content has been predetermined from the obtaining of the soil sample pa lang. Now that would be all for the plasticity of soil. Now let us proceed to the structure of soil. Soil structure is defined as the geometric arrangement of soil particles with respect to one another. So among the many factors that affect the structure are the shape, size, and mineralogical composition of soil particles, and the nature and the composition of soil water. So in general, soils can be placed into two groups. We have the cohesionless and the cohesive soils. So let us first talk about cohesionless soil. So let us first define what is cohesion. No? Cohesion is the force that holds together molecules, or like particles within a soil. So the structures generally encountered in cohesionless soils can be divided into two major categories. We have the single-grained and the honeycomb. Single-grained structures, no, mo ni siyang nagkandalain-lain nga arrangement sa soil particles. So they have their name, and they have been classified into different structures. So single-grained structures are present in cohesionless soils like gravel and sand. So in single grain structure, soil particles are in stable positions, with each particle in contact with the surrounding ones. The shape and size distribution of the soil particles and their relative positions influence the denseness of packing. Thus, a wide range of void ratios is possible. So it could be this one, no? There are a lot of voids, and then in this illustration as well, ay pod ang positions sa mga soil particles. So nagkadepende sa iyahang arrangement pod ang void ratio nga possible nga ma-create. So to illustrate the structure for single grain structure, no, a real soil differs from. So this illustration simply means nga depende ra gyud sa arrangement sa soil particles ang iyahang cadense or ang iyahang void ratio nga ma-create. So kung if inani ang arrangement sa soil, butang nato yung void ratio is 90, meaning daghan jud siya, no? So on the other hand, kung inani pod ang arrangement sa soil particles, gamay ra ang void ratio, meaning mas dense siya, no? Mas compact, mas dugol ang mga soil grains, or they are in a dense state, or batang nato yung void ratio is 0.35. So compare nimo ang duha, mas dako gid ang void ratio ani nga arrangement kaysa ani nga arrangement. So real soil differs from the ecosphere's model in that soil particles are neither equal in size nor spherical. So the smaller size particles may occupy the void spaces between the large particles. Thus, the void ratio of soils is decreased compared with that for equal spheres. So however, the irregularity in the particle shapes generally yields an increase in the void ratio of soil. So as a result of these two factors, the void ratios encountered in real soils have approximately the same range as those obtained in equal spheres. So the second type of structure for the cohesionless soil is the honeycomb. No, in soil, the honeycomb structure is composed of the particles ranging in size from 0.02 to 0.002. Sa pino na kaya na sila, no? Which are often fine sands or silts. Allowing this sort of dirt to settle on the ground causes the particles to attract one another and form a bridge of particles. Additionally, a big vacuum is created between those bridges, which results in extremely loose soil in nature. The attraction of the particles is owing to their cohesion, but this cohesion is only relative to their size, and thus soils are not naturally plastic. So when water is introduced to dry fine sand, thickening of the sand occurs, which is nothing more than a honeycomb structure. Static load capacity of the honeycomb constructed soil is restricted. They are unable to withstand vibrations and shocks beneath the building and may use significant deformation or may cause significant deformations to the structure. So now let us talk about the cohesive soil. Kay cohesionless mo no? This time we will be talking about the cohesive soil. So to understand the basic structures in cohesive soils, we need to know the type of forces that act between clay particles. So when two clay particles in suspension come close to each other, the tendency for interpenetration of the diffuse double layers results in repulsion between the particles. At the same time, an attractive force exists between the clay particles that is caused by van der Waals forces and is independent of the characteristics of water. Both repulsive and attractive forces increase with decreasing distance between the particles but at different rates. So when the spacing between the particles is very small, the force of the attraction is greater than the force of the repulsion. So these are the forces treated by colloidal theories. So local concentrations of positive charges occur at the edges of the clay particles. The clay particles are very close to each other. The positively charged edges can be attracted to the negatively charged faces of the particles. Let us consider the behavior of clay in the form of a dilute suspension. So when the clay is initially dispersed in water, the particles repel one another. So this repulsion occurs because the larger interparticle spacing of the forces I know the forces of repulsion between the particles are greater than the forces of attraction. So the force of gravity on each particle is negligible. Thus, the individual particles may settle very slowly or remain in suspension. So there are different types, no, of structures for our soil and the cohesive type of soil. So let us first talk about the dispersed structure of soil. So the sediment formed by the settling of the individual particles has a dispersed structure, and all particles are oriented more or less parallel to one another. So mo ni siya may tabo daw sa structure of the soil when diluted no in water. Mo na siya. So if the clay particles initially dispersed in water come close to one another during random motion in suspension, they might aggregate into visible flux with edge-to-face contact. In this instant, the particles are held together by electrostatic attraction of positively charged edges to negatively charged faces. So this aggregation is known as flocculation. When the flux become large, they settle. So again, when the flux become large, they settle under the force of gravity. The sediment formed in this manner has a flocculent structure. So this is a flocculent structure of soil. No. Okay. When the salt is added to a clay water suspension that has been initially dispersed, the ions tend to depress the double layer around the particles. This depression reduces the interparticle repulsion. The clay particles are attracted to one another to form flux and settle. The flocculent structure is shown here with of the sediments formed is shown here then. The flocculent structure. So, kato kaganiha is the flocculent structure before salt is added. And this one, we have the flocculent structure of soil when the salt is added. So, due to the addition of salt no into the water, the ions tend to depress um, the double layer around the particle. So, causing a weaker interparticle repulsion. So let us talk more about clay because most of the time clay are considered to be a cohesive soil. So clays that have flocculent structures are lightweight and possess high void ratios. So clay deposits formed in the sea are highly flocculent. Most of the sediment deposits formed from fresh water possesses an intermediate structure between dispersed and flocculent. So a deposit of pure clay minerals is rare in nature. So when a soil has 50% or more particles with sizes of 0.002 millimeters or less, it is generally termed clay. So studies with scanning electropic microscopes have shown that individual clay particles tend to be aggregated or flocculated in submicroscopic units. So these units are referred to as domains. The domains then group together and these groups are called cluster. Clusters can be seen under a light microscope. So this grouping to form clusters is caused primarily by interparticle forces. The clusters in turn group to form a ped or form peds. Now, peds can be seen without a microscope. Groups of peds are here shows the arrangement of the peds we have here and macropore spaces. So the arrangement of domains and clusters are sealed particles with sealed particle sizes is also shown. So we have here sealed. So I guess that would be all for the discussion of the plasticity and structure of soil. Thank you so much.